Good afternoon and welcome to Math and Engineering Help Desk. Today we're going to have part one of a final exam review dealing with the first 3 units in our Connecticut State curriculum of review, which is patterns, equations, and functions, actually, and inequalities as well. So we're just going to go through all these different questions that I have featured on here, and we'll go over the answers and we'll talk about topics as they come across. So in the first unit, we're talking about using patterns and using different stages and writing rules, recursive and explicit rules to discuss these. So we'll talk about a couple of different things as we go through this particular unit. Starting here with, we have a pattern. We have a trapezoid here, we have 1 trapezoid here, then we end up with having 4 trapezoids added on, and then we have, it looks like 7 trapezoids. So the pattern here looks like it's a straight linear increase, and so if we had 1 trapezoid in the first, we would have 4 in the second, and it looks like we have 7 in the third. So basically, what's the pattern here? We're adding 3 each time. So in stage 3 we should have 10, and in stage 4 we should have 13. So that's how we fill that table out. Now, a recursive rule. So we have a couple of different strategies that we can use to write recursive rules. The recursive rule that we can use in regular equation language looks like this. A sub n equals and the way you write a recursive rule is you always would use the previous term in your rule. So using the previous term, what would you do to that previous term to get the next term? You would just add 3. So the recursive rule to describe this is like this. You also can say, for a recursive rule, our starting value, and then we're going to add 3 each time. That's kind of more like an explicit rule, but you also could say that as well. But this is an official recursive rule to explain this pattern. So we use the current term is the previous term plus 3. Does this pattern represent linear or exponential function? This represents a linear function because the increase is added to get the next term. All right. Whereas if it was multiplied, it would be an exponential function. Okay. Now, we write an explicit rule that uses function notation for this pattern. So now, with the explicit rule, this is where we would use the first term to decide what the next term is. So basically, the a to the n, which is our function notation here, would equal, in this case, we would have our a sub 0, which is our initial term, plus, oops, my subscript thing, plus, and then what are we increasing by? Well, remember the rule here is we're going to be taking the nth term and multiplying it by 3, because every time the increase is by 3, we would have 3n. Now, I want to address one thing, because I know that in prior examples and prior things with this unit, we have talked about using n minus 1 here, but the reason we're not using n minus 1 here is because the 0th stage is included in the table. So if we were to use n as our stage number, we would just need to use the current stage number to get our increase. And here's what I mean. Our 0th number is 1, right? So if our n is 0, this is going to be 3 times 0. So we just left with the starting value of 1. Whereas here, if we go to the first stage, n would equal 1. So it would be 3 times 1 plus 1, which is 4. So every time no matter which n we use, this would basically give us that value right away. Okay, so that's our explicit rule. And then lastly, we just need to find f of 12. That means we're going to plug in 12 for this function. So it's going to be equal to 1 plus 3 times 12, right, which is just 37. So the 37, so at the 12th stage, you would have 37 trapezoids. Okay, let's go to the next one. Another kind of similar thing. So here we get, and by the way, you can see this is color, which is nice. The printouts were all black and white that I had given my students. So stage 0, at stage 0, what do we have? Well, total number of chips in the stack is going to be, it looks like 3. So our starting value is 3. And then we end up having 6. And then we end up having, at stage 2, we would end up having 12, because we're basically getting the same, we're increasing both stacks by the same amount. And then stage 3 would have 24, and then we would have 48 for stage 4. Sorry for the not vertical alignment of this cursor. It's not exactly exact. That's okay. All right, so a recursive rule for this pattern. So again, how are we determining what the new term is if we had the previous term? Well, what we would do is we would have a sub 1, a to the n minus 1, which means the previous term, and then we would be multiplying it by 2, right? Because our next value is basically the double of the previous value. So if I took the previous value and just multiplied it by 2, I can write that. I also could, in addition to writing it like this, I also could just write 2 times a minus 1. I also could write that. I could also put in print or just next to each other. I don't even need to do that, right? I can write either of those. Okay? 2an minus 1 is kind of the same thing. So we take the previous term, we double it. Does this pattern represent an exponential or linear function? This is exponential because a common ratio is used. And also, I want to show you one thing I just kind of reminded myself of, because I'm reviewing this as well. We can say the increase is added to get to the next term. We also could use the vocabulary associated with that because there is a common difference, okay? Which means that the same number is added or subtracted to both to the numbers to get that. Okay, so going back to this problem, it's a common ratio. In this case, the common ratio is 2. So an explicit rule for this in function notation. So the same deal here, a sub n, a to the n, excuse me, equals our initial term, which is a sub 0. In this case, it's going to be plus or multiplied by multiplied by times, in this case, it's going to be 2 to the, oops, there's my superscript, n, not that, nope. I want that as a superscript. There we go. Okay. Times 2 to the n. So basically it's, and then if I want to obviously use the correct values for this, which I probably should do for the other one as well, that means that a sub n in this case would equal, a sub n is 3, so it's times 2 to the n. Let me go back to the previous one and check that as well, because I don't think I did that. Yeah, I left the a sub 0 in there. So basically that's going to actually be 1 plus 3n. Okay, there we go. Fix that. All right, and then lastly, f of 6. So we just have to basically plug in 6. So a of 6 equals 3 times 2 to the 6th. Okay, well, 2 to the 6th is 32. And 32 times 3, no, I'm sorry, 2 to the 6th is 64. 64 times 3 is equal to 100. 64 times 3 is 192. Okay, which makes sense because if this, look, we're at the fourth stage here. Fifth stage would be 96, and then if we double 96, we get 192. So that works. Okay, so that takes care of our Unit 1 review. Now let's solve some equations and solve some inequalities. So if we have x over 5 equals 7, the proper procedure here would be to multiply both sides by 5, because we would be undoing the multiplication, undoing the division of 5 by x, which means that our result here is x equals 35. Not 325, 35. For number 4, we're going to want to distribute this 3/4 to everything inside the parentheses. We alternatively can divide this off right away, and we can get a number here as well, and then just solve this inside. So either way, we kind of the same level of steps as either way we do it. So 3/4 times 4 is 3x, plus 3/4 times 8 is 6, and that would equal 12. Then what I would do here is, if I reverse my steps, I'm going to subtract 6 on both sides, and then I'm going to divide the result by 3. So that means that 3x would equal 6, which means that x equals 2. Okay, so the value I would use here is 2. Now, I'm doing the review of just going through solving the problems. It is good practice to always plug this back in and make sure that you get the right answer, make sure you get the same thing. So 4 times 2 is 8, plus 8 is 16. And if I did 3/4 of 16, I would get 12. Okay, it's good practice for you on a test to make sure that you check your answers by plugging in the solution you get into the original equation to make sure it works. Okay, so same deal here with number 5. We're going to distribute the 9. We also could divide it off and solve the equation inside. That's all acceptable as well. Just to show you that we can do that, I'll do that for this problem. So let's divide both sides by 9, because we can do that. This is a multiplication problem. I can divide by 9 to get rid of that multiplication and leave myself with the other factor. So in this case, the other factor is 2x minus 3, and that would equal 5. Then to solve this equation, I would just add 3 and then divide by 2. So if I add 3 here, that's going to give me 2x equals 8, which means x is going to equal 4. Okay. All right, and then again, just as the same as before, I want to plug that in and make sure it works. So if I did 2 times 4, that's 8 minus 3 is 5, and if I did 9 times 5, that equals 45. Okay, perfect. Now for number 6, the proper steps and proper idea here is that we want to get the x's on the same side. So if we have a 5x here, we have a 2x here. I've taught with my students to use the lower coefficient of x to move that term over. So if I've got 2x here, to move 2x, I'm going to subtract 2x. And by using the lower coefficient, you're pretty much guaranteeing that you're going to have a positive coefficient of x. You don't always do that, and matter of fact, no, you will always have a positive coefficient if you do that. So if you always use the lower coefficient of x to decide which of those terms you want to move over, it'll give you a positive x that you can work with. So in this case, you're going to have 3x minus 4 equals 11. And then the same steps that would apply here. This is just a regular two-step equation once you've done that. So we'll add 4 to both sides. That will be 15, and then 3x equals 15, which means x would equal 5. So 3x equals 15, and then x equals 5. All right, and then again, plug it in to make sure that it works. Sorry, my mouse is kind of waking out a little bit on me. So let's check this out. If I do 5 times 5 is 25, minus 4 is 21, so 21 over here. And then if I do 2 times 5, that's 10. 10 plus 11 equals 21, so I get 21 on both sides. I'm good to go. All right, number 7. This time we're going to distribute the 6. This time we want to distribute the 6. We can't divide that off because I'd have to divide 4x by 6, and that just makes things a little harder for me. So I'm going to distribute the 6 first on the right side. I'll leave the 102 alone for now. That is equal to 6 plus 12x plus 4x. And then if I combine my x's, that's 6 plus 16x. And what does that equal? It equals 102. So now, to solve this particular equation, I'm going to have to subtract 6 first and then divide by 16. So 6 goes away from here, and then I'm going to have 16x equals 97. I'm just going to reverse the terms here. 16x equals 96. So if I divide both sides now by 16, I will see that x will equal 6. Okay? And again, just to check, if I do 2 times 6, that's 12. 12 plus 1 is 13. And that 13 is then multiplied by 6. That is 78. That's 78 plus 24. That does equal 102. All right, number 8, same kind of deal here. We have some distribution to do first before we collect some terms. So let's distribute that left side. Negative 7 times negative 6 is going to equal positive 42. Positive 42 minus 56x, and then plus 3, right? So that's going to be that left side. And if I combine the 42 and the 3, that's going to be 45 minus 56x. And that equals my left side still, which is negative 16 plus 5x. So just as before, if I use the lower coefficient, it is easier to move that term over to the other side. So in this case, negative 56x is the lower coefficient, and you want to add that to both sides. So we'll add 56x to both sides. 56x and 5x is 61x on the left side, so that's going to be negative 16 plus 61x, and that will equal 45. And then see here, what I'm going to do is I'm going to add 16 to both sides. That's going to give me 45 plus 16, which is 61, excuse me. So 61x equals 61, which means if I divide off, I'm going to get x equals 1. Now be careful, just remember, dividing 61 on both sides cancels 61 and 61 on both sides, but remember 61 divided by 61 is 1, not 0. So make sure you don't make that mistake. And then my x equals 1, if I plugged it in to check, I should get the same value. For number 9, we have fractions. Don't get scared of fractions. The process is still the same. I'm going to add 5 to both sides. Now when I add 5 here, if I want to stick to fractions, I can't add 5. I have to get a denominator of 2. So I'm going to convert this to 10 over 2, which is the same thing, right? So if I make 10 over 2 and 3 over 2, that's going to be 13 over 2. And then that's equal to 1/2 x. And then if I want to clear that 1/2 out, and opposite of 1/2 is multiplicative of 1/2 is 2. So if I multiply both sides by 2, that would yield 13 over 2 times 2, which is just 13. So my solution here is x equals 13. All right, and that makes sense. Now alternatively, and I'll do that in the next problem here, another strategy that you can use when you have a lot of fractions inside of equation, excuse me, is to use the least common denominator, and you can multiply both sides by that least common denominator to clear out your fractions and make it so that only your answer would be a fraction. To do that, if we had 3, 7, and 2, the least common multiple of these numbers is if there's no common factors, there are no common factors at 2, 3, and 7. So to find the least common multiple, we just have to multiply all 3 of those numbers. So 7 times 3 is 21. 21 times 2 is 42. So if I multiply this entire equation by 42, that would clear out all of the fractions, okay? And it's easier than it sounds to do that. If I do 42 times 1/3, that basically is 42 divided by 3. That's 14. So that means 14x. And if I do 42 times 2, which is 84, 84 divided by 7, that equals 12. And of course, I can use a calculator to do that if I need to as well, right? And if I did half of 42, 42 divided by 2, that equals 21. So now I've turned this fraction equation into a regular two-step equation. So if I subtract 12 on both sides, that's going to be 9. So 14x would equal 9. And then 14 times what gives you 9? Well, to find out, we would divide by 14. So dividing by 14, now obviously here, you can't divide 9 by 14 nicely, so just leave it as a fraction. You don't have to turn it into a decimal. You don't have to give an unwieldy repeating decimal for 9 over 14. Just say x is 9 over 14. That's it. Okay? I read it as a horizontal fraction there, but you understand the difference between those, right? Same, well, no, there's no difference between those. X equals 9 over 14. Okay? So this is a little bit harder to check, but if you have a graphing calculator, just type in 1/3 times 9/14 plus 2/7, and you should get 1/2 when you do that. Okay, or 0.5 if you like decimals. Now, next one. Now we have, there's one more, I think there's one more thing on here. Yes, there is. Okay, on this page, there's a couple more, there's inequalities I wanted to show you. Okay, so when I have inequalities, I solve them the exact same way as I have equations. There is a spot to graph on your sheet. I didn't copy that part, but we'll draw the graph on here just to kind of illustrate that. 3x minus 5 is greater than 2 times x plus 1. This is an instance where we want to distribute because 2 divided off into 3 and 5 is not a nice number, so distribute this instead. So that's going to be 2x plus 2 on the right side, and then that will be greater than 3x minus 5. So let's write that. And then we get the same thing here. We want to just collect our x's to one side. So subtracting 2x from here and 2x from here is going to give me just regular x. That is going to be x minus 5 is greater than 2. And then if I just add 5 to both sides, I get x is greater than 7 for my answer. So now when I graph this particular solution, we're going to use a number line. So here's a number line. We can label two numbers on here. Basically, I like to label 0. You don't have to label 0, but I like to label it. That's just me. And I'll label 7. 7's my solution. Because it's greater than, I'm going to use an open circle. And I'm going to draw this open circle as best I can with my mouse. Let's see how I do. Not my best. That's okay. And then from that open circle, we're going to use a line. And I'll use a gray line here. And that gray line is going to extend. I want to extend one from that circle. And it's going to extend this way. Okay, so that's how you graph that. So it's an open circle because it's greater than, and then we extend to the right because it's greater than. Okay, and the last inequality on here, we have simplified. We'll have to simplify this left side first. Let's distribute -3. So -6 is still there. -3 times 5 is -15, so it's minus 15. And then -3 times 6x is -18x, so we'll write minus 18x. And that's less than or equal to -147. Just so you know, when you're in a programming days, when you had to write less than or equal to, this is the symbol you had to use to show that. Anyway, so we'll simplify the left side. -6 and -15 is -21. -21 minus 18x, less than or equal to -147. Now we'll add 21 to both sides. By adding 21 to both sides, I'll have -18x. Less than or equal to -21 plus 147 is -126. And then I'll divide both sides by -18. Now, this is an instance, this problem is on this review, obviously, for this particular instance right here. When I divide by a negative number, and this goes for multiplying by a negative number as well, in an inequality, because you are multiplying by a negative number, the inequality needs to flip, because by multiplying by a negative, you're effectively flipping your solutions in sign. So you're going to also flip your inequality for the same reason. So this is going to give us now x is greater than or equal to, okay? And also you could write like that as well, but that's okay. Again, that's sort of the programming syntax that you would use here. And that's going to be 7. And that's because a negative divided by a negative is a positive. Okay, and this is another instance where it's a good idea to check your solution. We'll graph the solution as well, and we actually can use this same exact graph right here. Let me see if I can even copy this. Let's see if I can do it. Yeah, it looks like I can. Let's clone this, copy it, we'll paste it in. Let's see if I can just do that. Oh, maybe not. Okay, it doesn't want to do that. But basically, it would basically be this graph, but with the blue circle filled in. Okay, is that okay? I think you can handle that, right? So same as this graph, fill the circle because it's greater than or equal to. Okay, now solving for the equations in either code. So this is the last page on this particular. Oh, we have one more page after this. Last section on here. Let's solve these equations for the variables that are listed. So I like to illustrate this using a flowchart, but you can use straight algebra here if you're solving for a variable. You just have to reverse the steps that happen to the variable to get the variable by itself. So one suggestion here is to use a flowchart. You've seen me use flowcharts in the past. So if I start with R, what happens first? Well, if you multiply it by 3, that would be the first thing that happens to R, and then you would add by S. Okay? And if you do that, if you take R, multiply by 3, and add S, that would give you D. Okay? So now if we want to go backwards, start with D, and we just have to reverse the steps that happened to R to get that, right? So instead of instead of adding S, we would subtract S. And instead of multiplying by 3, we would divide by 3. Okay? And that would equal my R. So this means basically that if I want to write this as a formula, I would have to start with here, and then write all these steps in order, preserving the order to get that. Okay? So that means for number 13, R would equal D minus S, and then divide the whole thing by 3. And that's what that would look like. 14, same kind of deal here. This time we have C. Well, what happens to C? It's multiplied by S and divided by D. So if I want to flowchart that, I can write C, and then I can write multiplied by S, divide by D. And in actuality, it doesn't matter which order you do that in. Multiplication and division are the same group. So kind of going left to right or up and down is the recommended procedure. So that would give me my R. So let's see if I can do this way, right? If I start with D, excuse me, C, and I start with R, what would I do? I would multiply by D, and I would divide by S. So just reversing the steps, right? So C would equal R times D over S. All right? For 15, same kind of deal here. B would first be multiplied by 3, and then we would have to add 2A and add C. All right, so we'd have actually 3 different steps. Sorry for the crunching up of the things here. But we'd have 2 things to add and then 1 thing to multiply by. So multiply by 3, then add 2A, then add C. That would give me P. So if I start with P, I would have to subtract C, subtract 2A, and then divide the whole thing by 3. And that would give me B. So that would be that. And then lastly, for 16, what happens to B? Well, B is multiplied by 1/2 and multiplied by H. So I would have to take A, and I would have to divide by H, and then also multiply by 2, because dividing by 1/2 is the same as opposite of dividing by, or multiplying 1/2, excuse me, is multiplying by 2. And that would give me the B. Okay? So again, you can use algebra to do that as well. You can divide by H, you can multiply by 2. The same thing would happen. Okay? Just reverse the steps that happen to the variable that you're trying to isolate. Okay, last part of this video is number 17, number 18 here. These are word problems, and these are pretty easy word problems when you break it down. Janet bought a new gym membership. Initial signing fee is $25. The fee for each month is $15, and she spent a total of $160. How many months did she have the gym membership? Well, the variable here is what is the amount of time, right? So the month. So in other words, if we start up with a $25 fee, and then $15 per month, so it's going to be 15x plus 25, and we're interested in when it would equal 160. So to solve this equation, we would subtract 25 and divide by 15, that it equals 9. So she has the solution, she has the membership for 9 months. If George ordered lunch, bought a hamburger for $4.50 and ordered french fries for $1.50 and to share with his friends, we spent a total of $10.50. How many orders of french fries did he order? So he ordered a hamburger, which was $4.50, and then he ordered an unnamed amount of fries. So that's 1.5x, x being the variable number of fries, plus $4.50, when does that equal $10.50? So again, if I subtract 450, that would be 6, then divide by 1.5, that would equal 4. So the solution here is 4 orders of French fries. Okay, so that concludes part 1 of this video. We'll be back with part 2. The rest of this review is a long review. We'll get it all done. Have a nice day.